Hey guys, here's your intro to arc length that you'll need to be able to do those problems. And the basic idea is it's exactly what it sounds like, except I'm going to start out with a linear function. And if I asked you to find the length from 1 to 5, I don't think we'd have too much trouble with that. So let's actually do it out. So let's see. Oh, I'm sorry. So this is y equals 2x. Let's just say 2x. So this is going to be 1, 2. This is going to be 5, 10. And I'm hoping everybody can find the distance between 2 points along a straight line. And you could either use the distance formula, which I'm going to use, or technically you could turn this into a Pythagorean theorem problem, right? Which is essentially where the distance formula comes from. So the distance would be the square root of 10 minus 2 squared plus 5 minus 1 squared. And you'd get 64 and 16, so square root of 80. Okay? If you have to simplify it, I guess you could. Let's see, that'd be, 4 radical 5? Okay? No big deal. But, unfortunately, we're going to have problems that will most likely look like this, where you're going to be asked the same basic question to find the length of the curve from 1 to 5. Unfortunately, if it's not a perfect circle or something like that where we could use like circumference, and if it's not a straight line, then we really don't have much of a chance. So we need to come up with a way to find what we call the arc length, sometimes referred to as usually just L. Okay, so let's actually, I'm going to put this to the side and draw this a little bigger. Let's just focus in on our old friend y equals x squared from 1 to 5. Okay, obviously if I just connect the segment from 1 to 5, right, I'm clearly not going to get the exact length of the curve. So what if I broke it down to smaller pieces and I found that distance? Well, that's probably pretty close to the actual distance of the curve, but it's still not perfect. But if I just, the idea of just breaking it down into smaller pieces is exactly like how we dealt with, our area situation. And eventually, you break it down into as many pieces. The more pieces you break it down into, the more likely those little segments are going to start looking like your curve. So that's essentially the idea of what we're going to do here. We're going to use the distance formula, but we're going to use it over an entire interval. Okay? So let's see, we've got the distance is the square root of, let's just pick two arbitrary ones. Let's call that, x1, x2. Okay? So this would be y1, y2. So my distance would be x2 minus x1 squared plus y2 minus y1 squared. And that's just this, there's just this piece right here. Okay? Well, obviously we need to connect this somehow to what we've done. And we've dealt with x2 minus x1 before, and we like to call that delta x. And we've dealt with y2 minus y1, and we've called that delta y. Okay? Well, thank you, Skittles. I don't think we need you today. Okay. Let's see. So if I just replace that for the moment, I've got delta x squared plus delta y squared. Okay, now I'm going to do a little bit of shenanigans, because that's what we like to do here in calc. And I'm going to sort of multiply through by delta x over delta x. So delta x over delta x. So I'm not changing anything, I'm just rewriting it. Delta x squared plus delta y squared. Well, the delta x that's in the numerator I'm not going to do anything with, but the delta x that's in the denominator, I actually want to bring it into the square root. So if I want to bring the delta x into the square root, I kind of have to turn it into a square root of delta x squared. Right? Square root of delta x squared, of course, is still just delta x. And that'll allow me to bring it in. We did something like this when we did limits. When we did looking for horizontal asymptotes. Remember, we would divide the numerator and denominator by the biggest power of x. Sometimes we had to do this little trick when there were square roots involved. Okay, so this turns into delta x square root delta x squared over delta x squared, and it's delta x squared, right? It's not just delta of the x squared, plus delta y squared. Okay, and there's my distance. And let's see, I'll just move this to the side a little bit. See it? Okay, clean that up. So my distance is going to be, and I'm going to just rearrange this a little bit, square root delta x squared over delta x squared, of course, is just 1, plus, oh, I forgot to put it over here too. Again, I'm sure you guys were just chomping at the bit to say something on Edmodo, but I caught it, as I always do. So there's my delta x squared, and so now I have delta y squared over delta x squared. So that's the same as delta y over delta x quantity squared, and then I'll put my delta x out here. Okay? Delta y over delta x, isn't that the actual derivative? Isn't that basically dy over dx? So I should be able to write f prime of x squared, and that's a reasonable substitution. Okay, again, dy over dx is the derivative. And then delta x comes along for the ride. So all we did, really, we found the distance between these two arbitrary points and just simplified and rearranged until it was something convenient. This is the same as just finding the old-fashioned distance that you did in Algebra 1. But I want to find a whole bunch of them. I don't want just this one. I want this one, and this one, and this one, and this little one, and that little one, and this little one went to market, and that little one went all the way up. No. So I want all of them. Well, we have a good technique for accumulating a whole bunch. We could do it in sigma notation, but my guess is you'd rather do it like this. Use the integral from the lower limit to the upper limit, square root of 1 plus f prime of x squared, and instead of delta x, I'm going to write dx, and that looks just like a formula we can use. Okay, so let's, just for the fun of it, let's go back to the beginning. Let's go back to this example here and check it out. If the distance is the integral from a to b of the square root 1 plus f prime of x squared dx, I should be able to find the length of a segment using the same method, right? I know it seems silly to do anything more than just what we did originally, but let's just see it work. So this is going to be from 1. This is going to be from 1 to 5. Square root 1 plus f prime. Alright, so y equals 2x. Y prime is 2. So that's 2 squared dx. 1 to 5 of square root of 5 dx, which is x radical 5 evaluated between 1 and 5. 5 radical 5 minus 1 radical 5, which is 4 radical 5. Okay, let's do it on the actual curve. Well, the distance is going to be from 1 to 5 of the square root 1 plus, this was, I didn't write it, but I'd said it after. This is y equals x squared, so y prime, of course, is 2x. 2x squared dx. Okay, so distance is going to be from 1 to 5, square root of 1 plus 4x squared dx. And unfortunately, we do not have a trick for that at the moment, so we could just use our calculator to figure that out. Okay, so hopefully you remember how to use your calculator. So let me get mine over here. Alright, so y equals x squared. I'll put that into my y1. And let's see, I think it was math 9. FNINT. Get my y variable, comma, let's see. Oh, sorry. Going too far old school. 9. Let's see, we need the square root of 1 plus 4x squared. So square root 1 plus 4x squared, close the square root, comma x, comma 1, comma 5. And this is approximately 24.4, or AP style, 24.395. Okay? So again, it's just the integral of the square root 1 plus 4x squared. So it was the integral of 1 plus f prime of x squared, and evaluated between 1 and 5. Okay? If for some reason you had to do this the other way, if they gave you it like as x equals, square root of y, and you didn't feel like converting it, you could do the same thing. You just have to use the y values. In this case, you'd use from 1 to 25, and you do the same exact thing. Okay? Hopefully that's enough to get you through. I will try to do a little bit more of the AP style ones when I get a chance. But if you have any questions, please post them, and I will talk to you guys later. Bye.